Thank you for the kind introduction. Yeah, the thesis that I am presenting here is called the Field Petrologic and Detrital Zircon Study of the King Sequence and Calaveras Complex of the southern Lake Kaweah roof pendant of Tulare County, California. Obviously, that's a specialized title, but it's really dealing with, I think, a very interesting period in the geologic history of the Southwest. This is a time where we're looking at the transition from the Permian and the era of a passive margin along the coast of the Southwest and the Laurentian continent, and its transition to an active margin with plate subduction and a period of magmatism and faulting. So there's a lot going on at this time. And it's an interesting time to study, an interesting story, in part because a lot of the evidence that is out there is hard to find. It's been covered up by the magmatism, the faulting, and the translations that have taken place. So it's a difficult area time to study just because some of the evidence a lot of the evidence is missing. We just have fragments here and there. So what I'll look at, we're going to do is do the background, which I just did. We'll look at the study area, which is called Limekiln Hill, talk about where that is. We'll do a little bit of regional geologic history that links to why this area in Limekiln Hill is interesting. And look at the rocks in the study area, the different rock units and what they tell us. These rocks have issues, so we'll take a look at those. And got the research methods that we use to try and understand these rocks a little better and the results of those issues, the results of those rocks, the studies and the analysis and what we found. The study area is, you can see, is located actually in the foothills of the Sierra Nevada. You can see we're located, it's an area, Limekiln Hill is adjacent to a dam called Terminus Dam, which is forms a Lake Kaweah. You can see in the upper right where the metamorphic rocks are that remain from the magmatism and the denudation created from the period of magmatism that we talked about, I just mentioned in the Mesozoic. Kind of looked at that little, you can see a little box there in that map of the Sierra Nevada batholiths, and that's pointing to this area here. It's a bit of a crowded map, but you can barely make out the names of some of these roof pendants, the remainder of the rocks that took place, the rocks that were laid out and remain partly from this period of time that we're very interested in. And we see this Boyden Cave, that's called a roof pendant. One that's left, we'll be talking about that. The Sequoia roof pendant, this is in Sequoia National Park. We got Kings Canyon National Park is right up here. Lake Kaweah roof pendant is right there. That's my study area. And we're going to talk about another roof pendant called the Yoko Valley roof pendant. Here's a aerial view of the study area. This here is Limekiln Hill. It's called Limekiln Hill because it's had lime kilns from when they were excavating marble here to bake and cook, make lime. Terminus Dam, Lake Kaweah. We have, what makes this area very interesting is a very large spillway that was cut through these rocks. And you can tell here that these rocks are fairly heavily covered. They're metamorphosed. So it is difficult to interpret these rocks, and that's characteristic of the area. So when we see the spillway, that opens a lot of opportunities to see how these rocks are related to each other. And it's a very large exposure, which we'll talk about. Here's a little bit of a close-up of the spillway. You can see the dimensions there. This is a part of the spillway way. You can tell here that they've built up these things called fuscates. They're designed to collapse when the lake level gets too high. They add 23 feet to the level of the capacity of the lake, and that's a good thing because these break instead of the dam breaking if the lake level gets too high. Here's another picture of the rock exposure that we get to use for the study area. Again, here's the north wall, south wall. You can see quite a bit of different types of rock units that are exposed. And what we're interested in is what these are, where they came from, but also how these rock units related to each other. There's my car there for scale, so you get the idea of the size. That's about 60 meters of height. So it's taller than it looks because it actually goes back. So this goes back, and it has a taller height than what you would think. So let's talk a little bit about the history. And where I'm going to start is back in the Carboniferous to Permian times, when we were just starting to have this transition, right, of going from this passive margin area to an active margin area. We've got this transform that some of you may have heard about, called the California Kaweah transform, taking place where a part of the Laurentian continent is being sheared off by this faulting activity. There's not a lot known about this, but some people attribute this faulting activity to offsetting this plate here called the Caborca block by about 1,000 to 1,200 kilometers. So some people say that it's a very active piece of activity. Our study area is right about there. You can see this is an entire continent-wide transform that's taking place. Now, kind of zooming in to our study area, which is right around in, say, San Francisco Bay, right up where that triangle. This is where you see this strike slip fault. That's the transform that we were just discussing, right? And what is interesting here is that my study area is right now kind of like under the ocean, right? It's this area called the Foothills Ophiolite Belt. And we're in the Permian about right now, right? And this belt has got a lot of pelagic silicates. We'll talk about those. There's blocks of limestone in there, upper oceanic. Lithosphere is part of this block that's coming in, and it's being accreted here to the coast, and you can see what's going on. So here's this truncation again. That's the California Kaweah transform taking place, a truncation. A little bit of continent on the side here, and here is this foothill suture docking against the continent. And some of you might have heard this foothill suture, also known as this strontium 87, 86 isopleth. You hear about that? Well, that's this suture right here. On this side, we get the ophiolite related rocks. On this side here is more of the continental type of rocks. And right here is a area where we call the Calaveras Complex. These are the depositional rocks. And so you got ophiolite down here, which is your upper lithosphere type of rocks, and melons and things like that. That up here is where you've got the silicates that are deposited on there, and limestones that have deposited on top of them. That's these rocks right here. And that's the docking. These are the kinds of rocks that I'm interested in my study area. This accretion event, according to a model by Jason Salibi, 2011, it's a model that Jason Salibi has been working on for a couple of decades, I would say, is accretion. He's got nailed down to a period of about 255 million years ago. That date relates to the docking that took place in my particular area. Okay. So going back to where we are, the study area that I've been doing, it's a I was looking at all the rocks that were in this zone here. And so this is the map that we looked at. And so these are some of the key rock units right here. With Metachert, we'll talk about that. That's these bands of what I got are kind of this orangish material. We got calc-silicates. These are minerals that are combined of silica-related materials mixed with calcium-rich materials. And there's marble in there, so we know the calcium came from limestone. And so there's marble blocks, and we'll look at that. And there's this massive biotite, and we'll talk about that. Okay. And biotite quartz schist, so we'll talk about that a little bit later. So that's our Calaveras Complex, defined as Permian to Middle Triassic. Okay. Pelagic, Radiolarian Chert, talk about that, the limestone, all highly metamorphosed. That makes it difficult to study. You lose a lot of information, obviously, in that recrystallization process. But there's still a lot that we can learn about. My favorite rock is the Radiolarian Chert. This is rock that is from deep marine environment. It's deposited over very long periods of time by gradual settling of small creatures. These are the skeletal remains that are made out of silica, not carbonates, of the size that you can tell, very small. People have estimated that each of these bands, here you can see it in chert, in its original form. This is from Marin County. When it's metamorphosed, what we've got into quartzite, this is what, from eyesight, this is what it looks like. Each of these bands represents, according to some studies, 10 or 20,000 years each, so it's a long period of time to each band. One study, and some others have linked these to Milankovitch cycles with 20,000, 21,000 year cycles, so each band would represent 20,000, 21,000 years. And it's a diagenic process that emphasizes these bands. And it's kind of interesting, these bands don't have, there's a lot of wrinkling going on, but they usually don't have any cleavage or cracks, so many specialists believe that this banding takes place during slumping activities when the rocks are still soft. In other words, it's not a tectonic event that creates this. But others disagree, so it's open to discussion. This is just another close-up. That's a little bit unusually thick. Usually it's not that, the separation is not that thick. But here again, you can see how the silica and the argillite, it kind of separate over time. This is just like it's the same process that creates chert nodules and chalk and limestone. Silica and calcite don't like each other. They're incompatible. So there's a separation process that takes place that emphasizes their differences, let's say, and creates this banding effect. There's also we also find a lot is this massive biotite quartzite, and I'm just interpreting that as a form that is either been altered. In some cases in my site, we've got this alteration from hydrothermal activity that's taken place probably a little bit recently that's altered some of that. But other cases, we have a chert-agellite mixture that doesn't have the right combination to form this pattern of distinctive banding, but nonetheless, perhaps because of the argillite density is too high, but very closely related. So we have rocks that are closely related, same depositional environment, maybe a slightly different mixture of the different types of rocks. Let's go to the calc-silicate rocks, which are also very interesting. A couple images there of the calc-silicates that are taking this banding, sometimes these banding does contain marble. Sometimes it's just different compositional bandings, different amounts of different minerals that have separated themselves over time through metamorphic processes. That's what we believe. Here's the calc-silicate. Huge number of, very interesting variety of minerals. And I just got, this is one that thin section's got most of the key minerals that we find in calc-silicates. Helps us to distinguish the calc-silicates from the other minerals that we find in the location. The marble lenses that come with the calc-silicates. So you can see calc-silicates are kind of embedded in the marble lenses are usually found inside the calc-silicates. And they're usually, they're all sizes, but many are very large. So this one here you can see is 10 meters. You can see that it is actually a bulging quality, that it goes from large to small very quickly. So the question is that we had to deal with what's going on here. Is that a deformation process? Was there a graben that this sank into? Was this a big block that fell down a hill in a submarine environment? So those were the kinds of things that we had that I was working on. In the marble lenses, there are very few fossils, but in fact, this is definitely the big stars of the find. But up on top, I found ones that I interpreted as gastropods. There's another one. There are a number of these that I took to be probably the same species of gastropod, all found in the same association. And then there's other fossils that I could not interpret that were interesting. Then in a separate location, an entirely different block of marble, there were these microscopic units that I and a couple others of us interpreted as cross sections of shells. But again, they're hard to interpret. You see, these are kind of at a almost microscopic level in terms of any detail you need in a microscope. Obviously, you see any detail. But at least this would tell us that these are a marble, at least this portion of the marble block is something that came from a more shallow environment. This is not necessarily a marble that originated in a deep marine environment that would be similar to the Radiolarian Chert, which by definition is deep marine and is lying right next to it. So that's an issue right there. There is this marble lens problem. One is that it's got fossils that are different from the environment that we associate with the banded chert. And there's also a marine chemical problem, and that is, well, there's more marble lenses. Let's talk about marble lenses a little bit more. These are the remnants of the marble quarries on the site. Here's another marble lens. You can get kind of an idea again of the size. This is another one on the opposite spillway wall. And you can kind of see here a little border that Diane found that kind of fringes this. So we looked at that. And that is something that has some of the qualities of the mantle that surrounds something called a listolith, which is a big block of rock that falls, that slides down through mass wasting. It could be in a big lithosome, a big giant rock fall, or it could be a gradual process from a high elevation, submarine elevation, or from the shoreline to low. So that we took as evidence that maybe these marble blocks are remnants of rock falls of some sort, or of mass wasting. That was kind of their interpretation there, my mass wasting. And these marble lenses are found in many of these roof pendants in the area. So, and that's a common interpretation, that they're list-to-list, and it's because of the same problems that we face, and that was, well, how do you get these marble blocks in this environment of a siliceous ooze that you would only find at very deep depths. And the reason that you only find siliceous ooze at deep depths is what we call the calcite carbon, the calcite what's it called? Yeah?
Compensation.
Yeah, the calcite compensation depth. And that's because at certain deep levels, and we'll go into that a little bit, the carbonates in a marine environment become dissolved in the seawater. They no longer exist as precipitates that don't reach the ocean floor. And so again, here we have, so this area here is entirely composed of metachert. We just mentioned that the silicates and the carbonates don't combine well. So when you see ribbon chert and there's carbonate in there, it's usually actually fairly easy to find the pieces of carbonate because they tend to blob together. And there's none in most of this. So you have ribbon chert, then you have marble. Well, these blocks probably came from up high, but then how about these big calc-silicate strips? Where did they come from? And we had kind of a graduated contact. That was kind of interesting, not expected to see. Where we have calc-silicates, and then you go a little bit more, and then you find yourself in a pure metachert environment. And meanwhile, in here, it's kind of a little bit, it kind of goes back and forth. That's kind of interesting. And so here's a graphic of the CCD, calcite compensation depth issue. And you can see from these depths, it's actually that cutoff between where you've got calcite and where you've got what we call the siliceous ooze. That banding is probably that we see there at the stripes. There's probably the ribbon chert is probably why they use that banding. I don't know that for a fact though. You see that we got depths of 3,000 to 4,000 feet. So the question is, okay, how do we get these calc-silicates right adjacent to these, all nicely lined up in smooth layers, right? So we got nice layers of the ribbon chert, even though it's contorted, and then we have the nice smooth layers of calc-silicates. Why are they right next to each other? And so we had to work with how that happened, especially since it seemed to be kind of like a graded environment. Like this is just like you kind of graded from this to that, and then went back and forth. And that was kind of a problem. And so one solution to that problem was maybe this CCD was going up and down at this particular area. Maybe this site was right at the location. It's not impossible. For one thing, the CCD does naturally go up and down over time with changing marine environments. It has historically been demonstrated that it does due to changes in marine environment and and marine currents. Also, it was close to, this was a time when, you know, with the Salibi model, that there was a large continental area accreting to the continental coast. So you're going to have changes in marine, the elevation of the marine floor going up and down as a consequence of that activity. So maybe it could happen. So that was one option, was that we had fluctuation in the calcite compensation depth that we were looking at. And the other was that we were looking at a different kind of a model where we had a more of that in association with these marble blocks, we had a carbonate rimmed shelf environment where we had sedimentary carbonates that were coming down in association, perhaps, with these giant blocks. So you can see these. If we have in this model here, we have the carbonate reef. This is the mud that gets produced at the top. Carbonate mud, this is deposition of carbonate-rich types of algae and the like that gets filled in a tropical environment. And this, the paleo latitudes are suggested to be that we are in a tropical environment at this point in time. And so that in association with blocks of limestone that we see, that there's episodes of, I would say, called turbidites or turbidity currents of lime-based sediment pouring down into a pelagic ooze. In this case, mixing with the radiolarian siliceous ooze that had, perhaps at this time, yet to solidify and lithify. So that's the other alternative model, which seemed to be pretty good because it carried some good weight. Also note the terminology here: resedimented carbonates. That is that these blocks and these and the sediments are not necessarily coming from the top and sliding all the way down 4,000 kilometers to 4,000 meters to the ocean floor. This is a process that could go in steps of sliding down, solidify, breaks up, and goes down too. Okay. So, looking at the Calaveras Complex in terms of where we are right now, in terms of the analysis, Calaveras, we've got a Permo-Triassic environment, a deep marine protolith, the siliceous ooze that we talked about. If, based on this model, we would have to be near, if we prefer the model, the depositional model, we would have to be near or in some proximity to either a carbonate reef complex or a shoreline complex, or at least near where one used to be, let's say. And that's good information to have. And we talked about that, and of course we have the interpretation of a litholiths and or lithostromes creating these large marble blocks based on the evidence that fossil evidence, and also supported by things like the suggestion of the mantle. And I'm not going to go into it, but there were other alternatives that Diane and I discussed quite vigorously that we ruled out over time to explain those litholiths, which explain the marble lenses. After the Calaveras settled down, there was another period of additional deposition that created a sequence called a King sequence that's also in my area. And this took place kind of upper Triassic, Jurassic time. Turbidites originating from the Laurentian continent. This limestone blocks as well. Here's one of them. Had volcanic, really volcanic clastics involved in there as well. And this turns out to have provided some additional information that was good in terms of our interpretation, and certainly what I'm proposing for the explanation of how we propose how we link what our findings were with the Calaveras complex to the model that is proposed by Salibi, which we will get to. There's a little bit more on the King sequence. You can see these are turbidites. These turbidites are actually a little bit different. They're actually, try to tell, we'll let's see if we can get a map here. These are separated. This is where the King sequence are in my area. These rocks are actually really don't have the folding and the same metamorphic grade that you see in these calc-silicates and metacherts up here that we associate with the Calaveras. So these king sequence turbidites are different. We have a fault here that's separating the two, and we're going to find out obviously these are but younger. So it was an interesting note and a piece of evidence that the deformational stage of these king sequence rocks is quite a bit different, in our interpretation anyway, than the rocks that we see up here. Some close-ups there. Okay, so there's more investigation to do. We looked at some of the methods there. We got the XRF. SEM played an important role, and of course we looked at radiometric dating. X-ray fluorescence. This is going to be real quick, guys. It's a process there where we use an X-ray source hitting a sample that causes the sample to fluoresce by the X-rays themselves kind of excite the electrons in the substances to higher levels. They go back down, causing a fluorescence activity. There are detectors that detect that fluorescence. They're set up in advance to detect certain specific wavelengths of X-rays that are characteristic of the elements that they are looking for in these, actually for a broad spectrum of elements. And they use that to detect both which elements are contained in these rocks, and they are looking at the quantities. An important point is that this analysis is actually for taking a large sample, powdering it down, and looking at mixing that sample very, very well, and looking at the chemistry of the general chemistry of the rock. So we're not looking at special minerals. We're just looking at the basic chemistry of the rock, the blended chemistry of the rock, let's say. Yep. And we get, very familiar, I think some of you are probably familiar, you get the oxides by the weight percentages. There's a lot of analysis that takes place in there. The one that was interesting was called this ACF diagram, the lumina, carbon, this lime or the carbon, and the ferromagnesian point here. The minerals that we found, or I found in the with the assistance of Diane, were these minerals in this area, all these kind of frontier minerals here. What was interesting on the ACF plot was the trend that we identified here on the ACF triangle. You see the calc-silicates seem to form a line. The marble, as you'd expect, all hit there at the extreme end of carbon like it was supposed to. But the calc-silicates seem to form a trend that is collinear to some extent. Looks a little bit collinear with both the rhythmic. This is the Metachert and the massive biotite quartzite, which we interpreted as the more Metachert or chert argillite, closely related. So we thought these fairly close line, and that we saw as consistent with that graded trend. You might recall I showed that what we noted was the contacts were surprisingly graded from, in not all cases, but in some cases, from a Metachert, from this Metachert composition to a calc-silicate composition, which was strange for me because the two environments are incompatible, and I would have normally expected, well, maybe I could expect a sudden transition due to turbidites, etc., but it was hard for me to visualize a gradual transition from a turbidite environment. But there was a gradual transition. Here, the chemistry even though there's not a lot of data points, in my opinion, but still the chemistry seemed to be consistent with this graded environment that we saw. Next we went to scanning electron microscopy. This is different in that here we are looking at specific minerals. We're looking at the composition of specific minerals, not the composition of the rock itself. And to be real quick on this, well, this is an example. We looked at garnets. Here you can see garnets in thin section are nicely formed in this particular case, the idioblastic. And here we see, here's the what we call the backscattered image of the same section. So this exact same garnets as they look in the backscattered electron image. This is the aspect of the scanning electron microscope where we just have a beam of electrons. They are deflected or reflected off the top surface of the thin section, right? And it takes the sensor or the detector, I would say, can form an image of how much or the extent to which those electrons are deflected. So if for dense objects like these white things, those are highly dense. That means they're used atoms that are with large nuclei, large atoms. And then quartz, objects that have smaller atoms, less dense material, those show up as dark. Zircons are dense, they show up as light. And let me just see. So here's data we get from a garnet. It just tells you the composition of each element that you see in your mineral. And then there's quite a bit of detective work to kind of break out, well, what is this stuff? It's not easy standing by itself to say, oh, well, this is obviously a garnet. There's a lot of analysis that takes place to decipher these things, because there's a lot of minerals. This being a calc-silicate, there are a lot of candidates of what these could be. But I found out that there's actually, what you can do is take subtotals. You look at the formulas for the epidotes, for the garnets, etc. You get the subtotals, and then you can get it there, and then you find your, you can classify your garnets in that way. And so there you go, and there's what we found in what I found in that particular slide. We also found epidotes that were rich in rare earth minerals. We use these mineral identifications to constrain the metamorphic conditions. And I'm going to just zoom in on this. And so we're looking at this area here. And the key index minerals are the staurolite, quarterite, diopside. Diopside helped us constrain the temperature. Quarterite kind of gave us a maximum number on the pressure temperature scale. The staurolite gave us a minimum. So I used that to kind of constrain the environmental conditions of the calc-silicates. The calc-silicates gives you more information for making that constraint than most of the other rocks that were there. So I used the calc-silicates to do that. You can see we have here's a pressure and GPA and a temperature. And this turns out to be higher than what I thought. So it was interesting. This tells us a little bit more about what we can expect to be preserved and not preserved. This might correspond to about 10 or 14,000 meters of depth, so it's pretty deep. Quite a bit of burial that took place in these rocks. Next, so that's kind of a highlight in terms of what we did with the scanning electron microscope, but there are others. Looking at zircons and the uranium lead dating, we got zircons. I think most of the people in the audience are familiar with zircons and how helpful they are in finding radiometric dating. So I won't go into a lot of that, but we take the samples from strategic areas. You take out the zircons. Happily, the zircons are extraordinarily dense, and they're about the densest minerals in a rock that are not magnetic, so eventually you get them out. They're placed on a puck, just like this one here. We go to the lab, in this case in LaserChron, which is in Tucson, Arizona. And we use a laser, and we take, what I do is I use this computer screen and the mouse, and you hit each of the zircons with the laser to take out the uranium and the lead isotopes. It goes through a device here with a plasma that strips away one or two electrons. That gives it a charge. That allows the mass spectrometer to separate the isotopes by mass, and that gets you the ability to count the isotopes because the different mass levels are directed to different detectors, and that way you can determine the ratios of how much uranium you have to how much lead. You adjust the lead for the natural abundances, and that'll give you a data set. So for the zircons and the set of zircons, what you get is actually two pieces of data within that set of zircons that are very valuable. One is you can help identify, or let's say you get the age of the zircon. Let's say for each zircon you get the age and you get the uncertainty of the age for each zircon, and usually you try to get about 80 or so zircons in the sample, so you have a generous supply. And you use that to constrain two things. One is the age of the sedimentary rock, and you use that to constrain, and we'll take a quick look at that, the provenance of where that sedimentary rock might have come from. In terms of the constraining the age, a key variable we get is called maximum age of deposition. And that is, we're looking at the youngest zircons in the set. So out of the 80 zircons, we would pull out, we kind of hope for like a group of 3 or 5 zircons all clustering around at the youngest portion of that set of zircons, and give us an age, what we call the maximum age of deposition, because the ages you have zircons that they're 180 million years old, you know that they weren't deposited before at 200 million years before the zircons were even made, and then that helps you constrain how the maximum age, in terms of how young that deposition takes place. That's a little trickier because you have to do some more additional analysis in terms of neighboring deposits and other ages to see if there was some gap between the time that those ages were, the zircons were deposited, or the time that last zircons were made, and the time that they were finally deposited. Okay, so these are looking at the samples we've got. The King sequence rocks, we have the age of 181 million years, plus or minus 3 years. So we've got a pretty good age on that. We've got 4 samples, 4 zircons, excuse me, in a nice, fairly nice, not too bad bracket. And that gave us statistically a fairly nicely bracketed area. And it turned out that that is not a surprising value for the King sequence rocks that we got. But what was surprising, or a little bit surprising anyway for us, is that in these Calaveras units, we did get we got zircons at all. It actually is very difficult. It spent a lot of time even finding any rocks with zircons in a Calaveras unit, and you can understand why, because you usually don't get deposition from terrestrial deposition in marine rocks, right, of that depth. So we have got 2 samples that did. One had a date of 271, but plus or minus 60. So you can see we had a nice sample here, nice selection of zircons, but very few young zircons. So the maximum age of deposition, not that well constrained, but it's still constrained at a time that is consistent with the Permo-Triassic aging of the Calaveras transition. So it's consistent, but poorly defined, poorly constrained, let's say. The other one is even more of a problem, because I only found 2 zircons that were in this minimum age bracket, and the second one was not a zircon with a very well-defined error bar. It had a pretty large error bar. So it says 233 plus or minus 3 million years, but that plus or minus 3 is a lie, because we really didn't have a good statistical base at all for that. So it's very, again, poorly bracketed, but still in this Permo-Triassic period time frame. So I just said, more or less 235 million years. And so here's where these rocks are located. The King sequence rocks down here. We had a small pocket of these siliciclastic rocks here, and here's a very small pocket again of these siliciclastic rocks. And I can't tell you how hard these things are. These deposits are to find. But these rocks are significant, and they are located adjacent to the Radiolarian Chert. So they're adjacent to deep marine rocks. And there they are, just little pockets. Here you can see the yellow here represents this. They call it a schist. You can tell it looks like a siliciclastic. So right there, you've got a clue that this is the kind of rock you want to look at. And then when you see detrital zircons, you know that you've got a siliciclastic rock. Okay. Okay. So this is just looking at the zircons in terms of the source. We've got 2 ways to do that. We've got these graphs where we look at the different distributions in terms of the age, right, and the cumulative probability associated with that age, overlap, similarity, and we'll take a look at what we kind of look at that. We have these, again, here we have age, and we have these age peaks, and the overlap and similarity look at the extent to which these different age peaks coincide with each other, correct? So we look at an age peak there, and if to the extent that they coincide, well, then that gives you a high score. Then going back, you can see here we have what are very high scores. Right. So what I did here in this step is comparing the younger rocks that are from the King sequence at the bottom with the older Calaveras rocks. And it was surprising that actually they correlated very well. Okay. Looking at the peaks there. After we'd done that, after I'd done that, I went on and looked at correlated these with rocks and other roof pendants to see what they looked like, to see if we can get a pattern in terms of matching the origins. And so I looked at some rocks and looked at quite a few different samples that were available to me. Found 3 roof pendants that had very similar samples. There they are, lining up the age peaks. These are for older years. Excuse me. Here we have going in the younger years. It got crowded, so I had to break it out. So here we have the younger periods of time breaking out the samples and the graphs. Again, we find some nice overlap. Boyden Cave, and I'll go back to show you where these are located. Yokel Valley, Sequoia. That's a Yokel Valley. That's one that didn't correlate very well. Here's one that correlated very well. Sequoia and Boyden Cave, and they're pretty far away, so I'll show you where these are. So we got Boyden Cave. So again, Limekiln Hill is down here. Yokel Valley, that's the one that didn't correlate so well. But we got Sequoia Pendant, very similar distribution of zircons. Boyden Cave, again, very similar distribution, really similar distribution of zircons, telling you that these units all shared a lot when it came to the origins of their siliciclastic rocks and their sandstones. Okay, so remember we had two purposes of looking at that. We wanted to constrain the ages. We got like a Permo-Triassic age in terms of the Calaveras. We wanted to constrain provenance. We saw that in terms of the Calaveras rocks. We have this Laurentian North American provenance. And we saw that they had a very similar, had a lot in common with the provenance of the Jurassic King's rocks, not just in Limekiln Hill, but by extension, a lot in common with other Sierra Nevada rocks that we found there in roof pendants and what we call Boyden Cave and the Sequoia roof pendant. And so going back here to the Celebi model, what we're finding is that this projected accretion date when this took place is consistent with the data that we're finding in terms of the detrital zircons. So we're finding that both the age of deposition of the Calaveras zircons are consistent with this accretion date, and we're finding that the provenance of those zircons is consistent with the fact or the concept that this accretion took place and it kind of been locked into place, let's say, at this period of time, because the provenances are of these rocks are so closely correlated with provenances of turbidites that are dated to much later dates, to these Jurassic dates. And that is what Diane tells me, is that when Jason Celebi heard that news, he was pretty happy about that, because he's kind of still working on data to support this model and this time frame and the like, and there's a consensus on this model is yet to be established. So that was one of the key findings of the study. Okay. That was I think time for me to wrap this up. And so I just wanted to state that I'm very grateful to an awful lot of people here in all the support I've gotten, both here at Cal State Fullerton and just a number of people here that have just been supportive to me throughout the time that I've studied here, that Diane has mentioned, both as an undergraduate, going through the undergraduate, since my background is in finance, I went through the entire undergraduate program. Nicole was actually the one who recruited me here first. So started out with talking with Nicole, and because I had to decide between Long Beach and Fullerton, and Long Beach has this huge lab with all these toys, right? And it's not like, it really doesn't necessarily belong to the department, but it's right next door. But this place looked better. So I decided to go to Fullerton. And just the teaching quality from Nicole and Phil and Brandon and Brady, and just to mention some of the teachers, just fantastic. So very, very exciting experience for me here. Really worth every minute. I was really happy that I did this course, we got the staff here, always very helpful. There's students that were helping me. See, I don't remember things quite as well as most other people here. I don't know why, but it just worked that way. And so much help from Michelle. I don't know how many of you met Mike Pryor, but he was helping me a lot in the field. Mike Martin did a lot of pioneering work in the Detrital Zircon here for Cal State Fullerton. He was a huge help. Ashley Melendez, I don't know if you remember here, but I was struggling in Brandon's mineralogy class. And boy, she helped me get through that. And then we were in the Grand Canyon. She helped me sort out with that. Natalie, been very helpful for me as well. The money came from the good folks at the American Chemical Society. So they get top billing there. But also, these are people that helped me in terms of supplying lab facilities, Detrital Zircon data. This is the SEM, LaserChron. This was access to the ranch site where I got some good Detrital Zircon data at the up in a study area just outside of the dam. Also wanted to thank the Terminus Dam staff. Went up there quite a few times, and they're always very helpful. And that's their guard dog, Sugar. But these guys were just amazing people. Of course, there's the family, the wife. She didn't like this picture. She had to sit on a rock. She hates rocks. She didn't always hate rocks, but it's something about the evolving decor of our garage, and now she hates rocks. That's, and my daughter Amy and my daughter Elizabeth, and also my mom there, who has always been an inspiration for me, and of course we've got our
nice picture.
Diane there. You can tell there, she's really out there to rough it there. That rock hand, that's a prop, by the way. But yeah, no, that was, she was always just a tremendous advisor. The advice that she gave me, one tip is that her advice on writing is excellent. And sometimes I think that the advice that you get on writing in the thesis process and the research is more valuable than what you learn about your specific topic, because so she's just excellent. And she doesn't make a big deal out of it. I think she's really good at that, and teaching the writing aspect, but also the research, always challenging. Any conclusion or any suggestion. If you make a conclusion, that's a big mistake, I'll tell you that. So that's just great advice. Just the incredible objective advice that I got, all the time was it's kind of hard to make that thing out there, but there it is. It was just always very well appreciated. So there we have it.